Picture this. It's August 6th, 1945, 8:15 in the morning. A brilliant, silent flash appears in the sky over Hiroshima. And in just a few seconds, the city is just gone. That was one bomb, at a time when only two existed on the entire planet. But today? Well, today is a whole different story. Yet today we are talking about over 12,500 nuclear weapons on Earth. And with that kind of number, scientists started asking a really terrifying question. What would actually happen if these were ever used? Their conclusion led to a concept known as nuclear winter. And get this, we're not talking about what happens at ground zero. No, this is the fate predicted for people living thousands of kilometers away from any blast. It's a global catastrophe born from a chain of scientific discoveries that changed our world forever. So let's back up and figure out how we even got to this point. Okay, first things first. To really grasp the scale of what we're dealing with, we've got to rewind. Let's go all the way back to the beginning, to when we first unlocked the power of the atom, and see just how much more dangerous things have gotten. Think about it. The bomb dropped on Hiroshima, again, one of only two in the world at the time. It killed around 140,000 people. Today's weapons, not only are there thousands of them, but a single one can be up to 80 times more powerful. We've literally gone from having the power to destroy a city to having the power to blot out the sun and trigger a global winter. So how on earth did that happen? Well, believe it or not, it all began with a few happy accidents. Yeah, the road to the atomic age was anything but a straight line. It was messy, full of detours, pure curiosity, a few lucky breaks, and all driven by scientists who, when something weird and unexpected happened, just had to ask, wait, why did that happen? So it all kicked off back in 1895. Wilhelm Röntgen is in his lab in the dark, and he notices this chemical plate just glowing. Turns out some mysterious ray was escaping his cardboard-covered equipment. He had no clue what it was, so he called them X-rays. Then, just a year later, another scientist, Henri Becquerel, gets annoyed because it's too cloudy for his experiment. So he shoves some uranium salts in a drawer with a photographic plate and forgets about it. But later, he finds the uranium exposed the plate all by itself. That was the discovery of spontaneous radiation. And that discovery, well, it lit a fire under Marie and Pierre Curie. They dove right into this new phenomenon and ended up discovering two brand new, even more radioactive elements, polonium and radium. And just like that, the door to a whole new kind of physics was blown wide open. Okay, so discovering radioactivity is huge, right? But it's one thing to know it exists. It's another thing entirely to figure out how to unleash its immense power. For that, you need a recipe, a set of breakthroughs that had to fit together perfectly, like the combination to a lock. And this is where it gets really cool, how all the pieces just clicked into place. First, you have the equation, Einstein's famous E=mc². That's the theory, right? It proves that a tiny bit of mass can be turned into a massive amount of energy. Okay, great, but energy from what? That brings us to step 2. The location. Ernest Rutherford figures out that basically all of an atom's mass is crammed into this tiny little nucleus at its center. So there's our target. But how do you crack that thing open? That was the key, the final piece of the puzzle. And James Chadwick found it. He discovered the neutron, a particle with no electrical charge, meaning it could just sail right past the atom's defenses and smash into the nucleus, splitting it apart and releasing all that energy. The recipe was complete. So once the science was figured out, things took a very dark turn very quickly. What started as a pure pursuit of knowledge became a desperate pursuit of power. The theoretical became terrifyingly practical as the world plunged into war. And the race for the atomic bomb was on. And what was driving this race? Pure fear. A physicist named Leo Szilard, who'd escaped the rise of fascism in Europe, saw the writing on the wall. He knew exactly what this new science could mean in the wrong hands. He was convinced that if Hitler's Germany built this weapon first, it was game over for the world. So he managed to convince the most famous scientist on the planet, Albert Einstein, to put his name on a letter to President Franklin Roosevelt. And that letter is what kicked off the Manhattan Project. But almost as soon as they started, the scientists stumbled onto a possibility so horrifying, it nearly stopped them in their tracks. It came from a calculation by one of the physicists, Edward Teller. He had this awful thought. What if the heat from the bomb was so extreme, so unbelievably hot, that it could actually set the atmosphere on fire? A chain reaction that would just wrap the whole planet in flames. And here's why they took it so seriously. Our atmosphere is 78% nitrogen. Teller's fear was that the bomb's detonation could kick off a runaway fusion reaction with all that nitrogen, essentially turning our entire planet into a small star. You can imagine the whole project just slammed on the brakes. So the job of double-checking the math, of making sure they weren't about to end the world, fell to the project's head calculator, a guy named Hans Bethe. He ran the numbers over and over and over. His final conclusion? The probability was almost zero. And that's what he told the project director, J. Robert Oppenheimer. Think about that phrase, almost zero, not zero. Can you imagine being Oppenheimer? That thought must have been a nightmare. They say on the night before the first ever test, he couldn't sleep at all. He just walked around the desert tormented by that tiny, infinitesimal, but world-ending possibility that Hans Bethe's calculation was wrong. Because if it was, it's not like anyone would be around to say, oops, my bad. Well, the test went off, and the atmosphere, thankfully, did not catch on fire. But in the aftermath of the bomb's use on Hiroshima, scientists started to realize a different, slower kind of consequence. One that would see the initial, unbelievable fire give way to a long, devastating ice. See, in Hiroshima, the explosion didn't just start a bunch of fires. It created something called a firestorm. The heat was so intense it sent a giant column of superheated air shooting up into the sky. This created a vacuum on the ground that started sucking in air from all around at hurricane speeds, which just fed the flames even more. The fire literally created its own weather system, a hurricane of flame pulling everything towards its center. And it was this completely unforeseen side effect that led a new generation of scientists to an absolutely terrifying new theory. Fast forward to 1983, a team of 5 scientists, and one of them was the famous astronomer Carl Sagan, that got together and asked a really big question. They said, okay, we know what one firestorm does, but what would happen to the planet if hundreds or even thousands of these things went off all at once in a nuclear war? They modeled it, and their paper, called the TAP study, gave the world an answer it wasn't ready for. What they found was just mind-blowing. They calculated that the immense amount of soot and dust from all those burning cities would be shot up into the upper atmosphere, and it would just stay there, blocking out the sun for years. So you could be in the middle of a beautiful, warm July day, say 25 degrees Celsius, and suddenly the temperature would plummet to -15. And the next month, -20. The entire planet would be thrown into a dark, freezing, artificial winter. The average drop in global temperature would be a catastrophic 25 degrees Celsius below zero. Now, to put that in perspective for you, the last actual ice age, that was only about 5 degrees colder than our normal climate. This would be 5 times more severe. And from there, things just spiral. It's a domino effect. No sunlight means no photosynthesis. Crops fail. Everywhere, which means mass famine, the entire food chain just collapses. On top of that, the blasts would create an electromagnetic pulse, an EMP, that would instantly fry electrical grids. So no power. Water supplies would get contaminated with radioactive fallout. Medicine, medical care, gone. It would become a world defined by cold and darkness and starvation. So all of this research led to this really stark, unavoidable conclusion. It totally changed how we think about nuclear conflict. It's not a war you can win. It's more like a game where no matter who starts it, no matter who you're attacking, everybody, and I mean everybody, loses in the end. And yet, despite knowing all this, governments are still planning for the unthinkable. They're making preparations like massive underground shelters, designing vertical farms that can grow food without sunlight, cultivating protein-rich algae like spirulina, stockpiling anti-radiation tablets, and trying to shield critical infrastructure in something called a Faraday cage to protect it from the EMP. This is what preparing to survive looks like. And that really gets to the core paradox of all this, right? A country could launch a perfect attack. They could completely wipe out their enemy. But the resulting nuclear winter doesn't care about borders. It would circle the globe and destroy their own civilization too. So you can defeat your opponent, but you can never, ever win the war. So when you really think about it, living in a bunker deep underground, eating algae, never seeing the sun again, if that's the best case scenario for the victors, it forces us to ask a fundamental question about the very nature of this conflict. What does it even mean to win?